everybody. Today what we're going to be doing is looking at 11.1. So go ahead and check out your warm-up and we'll go ahead and take care of this one together. So we're going to jump really far back and look at writing the explicit equation for each pattern. So these are most likely going to either be arithmetic or geometric sequences. So let's go ahead and look at this one. So if we notice, we start from here and we jump from 6 to 12, 12 to 24, 24 to 48. And as you can see, we're basically doubling each time. And you can see that that's also the growth factor by taking the next term and divide it by the prior term. Okay, so let's go ahead and actually look at this. So it says write the explicit of each equation. So right here, I know this is an exponential growth. And I know that this equation started at 6. So I know I'm going to do 6 times, and then whatever the growth factor is, which is 2, and then it's either going to be x or x minus 1. Remember, when it starts at 0, we're going to have it just be x, okay? And you can always plug in a few values to see if that makes sense and works. And for this instance, it does. So now let's go ahead and look at the next one. Here, we're actually shrinking. So to figure that out, what you would just do is take any of these two terms. You would take the second term, put it over the first, the term before it. So if I'm looking at these two, you take 12 over 36, and see that's 1/3. And if you would have done that with any of the values, you would have gotten 1/3. So this would just be f of x is equal to your initial term, which is 324, times 1/3, and since it starts at 0, we would just put x. Remember, if it was your first term, it'd be x minus 1. Okay? All right. So the sequence below exemplifies either an additive arithmetic or a multiplicative geometric pattern. Identify the type of sequences, fill in the missing values on the table, and write an equation. So if we go ahead now and look at this, here I go from 2 to 4, 4 to 8, 8 to 16. You can see I'm just doubling them. So I'm going to have 64, 128, and 256. So since I'm doubling these, it's going to be a geometric sequence. And then let me just double check. Did it want me to the equation? Let's see, recursive. Missing values of the table and write in the equation. It doesn't say which one, so I'm just going to go ahead then and write this as a explicit form. So this would just be f of x is equal to my first term, my initial, which is 2 times my growth factor. I'm doubling those. And then since I'm starting off at the first term, I would have x minus 1. Okay, looking like this. Okay, so let's go ahead now and look at the second one. Here you can see I'm decreasing. I start at 66, I go to 50, I go to 34, and then 18. So you can see I'm just subtracting 16 each and every time. So if I continue to do this, if I subtract 16 again, I would just have 2, negative 14, negative 30, and negative 46. Okay, so this is an arithmetic sequence. And the equation for this one will just be f of x is equal to, so my first term here is 66, so then it would be then negative 16x plus 82. So I got that 82 just by adding 16 to get what the 0 term would be, okay? And you can even just write like f of 1 is equal to 66. Okay, so let's go ahead and look at the final one. So here is a few ways to try to figure out and do it. You can go ahead and plug these into, You can plug them into a y equals mx plus b equation. You basically got 1 comma 3 here. You got 6 comma 96. That's one way to do it. But for me, I feel like this might be a geometric sequence. So what I'm going to just do is take 3 and I'm just going to double it. So I'm going to times it by 2 to get 6, 12, 24, 48, and if I double that again, I'd get 96. So the example I just used here, this was a geometric sequence. And the equation here then, once again, would just be f of x is equal to my initial, which is 3, times my growth factor of 2, and it would be x minus 1 because I'm starting off at the first term. You can even put f of 1 is equal to 3. So now what we're going to do is, so guys, just to give you a heads up, what we're going to be doing is looking at fraction exponents. So something you may not know is something like 4 to the 1/2. You can have a fraction as an exponent. This is always going to be your traditional power, and this is going to be your root. So basically what this is saying is 4 to the first power square root, okay? So you can do this with several different types of problems. So if you have like 2 to the 3 over 2 power, what this is saying is 2 to the third power and take the square root of that. So remember, this is the power, your numerator is the power, and this is your root, okay? So let's go ahead now and explore this idea. Let's take something that we already know that we just looked at, and it's saying they're exploring this bacteria, and the population of bacteria in thousands, what it's going to do, it's going to double each hour. So I'm going to have 8, 16, 32, 64,000 pieces of bacteria after 4 hours, okay? And we're going to take this idea here. So it says, write an equation for P, the population of bacteria as a function of T time, okay? So as you can see, it had a growth factor of 2. It was doubling every hour. So the total population is equal to my initial, which is 4, times my growth factor, 2, and then it's going to be, let's see, if it's going to be x minus 1, no, it's 0 hours, so it would be to x, okay? Or excuse me, we're going to use t for time. Okay, so that's going to show that I start off with 4,000 and I'm going to double every hour after that. So that's something we can agree on. But let's say this here. It says Travis and Miriam want to create a table with more entries. Specifically, they want to fill in the population of each half hour. Unfortunately, they forgot to make these measurements, so they decided to do an estimate to estimate the values. Miriam suggests they could fill in the data in the table following way. To make the estimate, I noticed that the population increases by the same factor each hour, and I think that this property could hold over each half-hour interval as well. Okay, so she's not saying they're going to double every half hour. Let me go and fill this out. So it says fill in the parts of the table below you've already computed in problem 1, and then decide how you might use Miriam's new strategy to fill out the missing data. As in the table in problem 1, each entry should be multiplied by the same constant factor in order to produce a constant results. Use the constant multiplier to complete the table. Also, plot Miriam's data on the resource page. On that resource page, guys, it's at the end of the lesson. It's just a table. You guys can go ahead and do that at the end. It will not be presented in this lesson, though, okay? So let's go ahead and talk about this. We already have this data filled out here, okay? And so previously, it went like just 0, 1, 2, 3, 4, and we had 4, 8, 16, 32, 64. That was what my previous table had. But now it's like, uh-oh. What we need to do is I need to figure out exactly what these half marks were. So in blue, what I'm going to do is I'm going to have my 8. On 2 hours, it was 16. 3 hours, it was 32. And 64. And to get from 0 to 1 hour, we multiplied by 2. I multiplied this 8 by 2 to get to 16. 16 by 2 to get to 32. Because what happened is it doubled each hour. But now I'm adding these intervals. So basically what this is saying, there's a few ways to look at it. I need to multiply to get to 8. I need to multiply this interval 1 time, and I need to multiply it again to 2 times. So what this is saying is I started off at, let me take a step back. What this is saying is I had a growth factor of 2, okay? And to get to that growth factor, I am now multiplying it by x and then x again. Well, why is it multiplying by x? That represents how many growth factors there are now. So I go up by 1, I go up again a second. So that's x times x. So if I take 4 and multiply it by a number, and I multiply it by the same number, I'm going to get to 8. So this would give me 2 is equal to now x squared. So then when I take the square root of both sides, it's going to get x is equal to the square root of 2, which means x is about 1.4142. Now remember that square root of 2 is an irrational number, and since it's an irrational number, it goes on forever, so this is an estimate, okay? Okay, so what this is saying now, it says on number 3, if we go back and look at number 3, it says let's fill this in now. So instead of multiplying every single number by 2 to get from 4 to 8, 8 to 16, 16 to 32, I am going to multiply everything by the square root of 2, by 1.4142 to get these values in between. So one more time, guys, remember we already know the growth factor was 2 to get from here to here. But now I'm not only multiplying the 4 by one number, I have to multiply the 4 by this 1/2 hour and the hour. So in order to get to doubling it, I had to multiply this same number twice. Okay, so I had to multiply it once, and then I had to multiply it again in order to get that growth factor of 2. Okay, that's how I got that. So now what we're going to do, though, is I'm going to take 4, I'm going to times it by the square root of 2. So you can use a calculator, or I'm going to go ahead and do it. I'm going to bring up my cell phone really quickly and show how I do this. So I'm going to take this 4, I'm going to multiply it by 1.4142, and I will get 5.66. And if I take this 5.66 and once again multiply it by the square root of 2, I'd get 8. And then I'm going to take 8, multiply it by 1.4142. This is going to give me about 11.31. If I take 11.31, multiply it by the square root of 2, I'd get 16. If I take 16 and multiply this, I would get 22.627. If I multiplied it again, I would get 32. If I took 32 and multiplied it by the square root of 2, I would get 45.25. Remember, these are irrational numbers, and these are about the correct answer. Okay, so there is some rounding there. So it says, what number did you use as a multiplier to complete the table in question 3? Explain how you found your multiplier. All right, so once again, if I looked at my original table, I only multiplied it from 4 to 8, I multiplied it by 2. From 8 to 16, I multiplied it by 2. From 16 to 32. Since I have these additional blanks here, I needed to multiply the 4 by the multiplier twice in order to get to 8. Okay? So essentially what I did is I know that these are my x values. I divided them by 4 and I get, hey, I get my growth factor, which was 2, but now to get to that growth factor of 2, I had to multiply the same number by itself twice. Well, x times x is x squared equals 2. So when I solve for x, I'm going to get x is equal to the square root of 2, once again, which is about 1.4142. That's probably the trickiest part, is figuring out the growth factor on these tables. So please, if that doesn't make sense, make sure you take note of that, and we'll go over that next time I see you guys. All right, so how can you use this equation created in question 2 to find in your table for 3 hours and for 7 over 2 hours? Okay, so if I were to look at this, it says for 3 hours, all I would do here, guys, is I have my original equation. So how can you use your equation that we created? So we had population is equal to, once again, we had 4 times 2 to the 3rd power. And then we also had P is equal to 4 times 2 to the 7 over 2. So when I look at this, guys, this is how I would do this. What I would have here is 4 times 2 times 2 times 2, so 4 times 8, which is 32. So I have a population of 32 in the thousands, so 32 thousands. Now how we do this is what I brought up, guys, is this is my power, this is my root. There are numerous ways to do this. So you can have 4 times 2 to the 7th power all over this and take the square root of that. So if I were to do this, it would be 4 times the square root of, if I look at this, I got a bunch of 2's. I can take out 1, 2, 3. So this would be 4 times 8 times the square root of 2, which would be 32 root 2. And guys, just so we know that we're doing a little estimating, we could do 32 times the square root of 2, which is 45.2544. Okay, so I just turned that radical 2 into 1.4142. So that's just one way to look at it. We can also do 4 times 2 to the 3rd square root 2. Kind of just factor it out what I kind of did over here. So yeah, there's just numerous ways to look at it. You can actually even write it as 4 times the square root of 2 to the 7th power. These are all just different ways to write the same exact one. So however way form works best for you, okay? So now what if you wanted even more detailed data? So what if Miriam wanted to estimate the population every 20 minutes instead of every 30? What multiplier would she use for every third of an hour to be consistent with the population doubling of every hour? Use the multiplier to complete the following. So same idea, guys. Once more time. I looked at my table for 0, 1, 2, 3, 4 hours, and I knew that this was 8. I knew that this was 16. I know that this was 32. So basically, to get from here to here, I multiplied by 2. I doubled it. So now I'm going to take this 4. I'm going to times it by an unknown multiplier to get to this value. I'm going to multiply it by the same unknown multiplier to get to this value. I'm going to multiply it by the same unknown value to get to this number 8. Okay? So basically, if I simplify this, I divide both sides by 4, and I would get x to the 3rd power is equal to, oh my goodness, that was my growth factor. Now I'm going to take the cubed root, and on this new table, when I'm looking at 1/3 values, I'm going to get a growth factor of the cubed root of 2, which is about, guys, and we're going to be rounding here, that is about 1.2599, okay? So that is my new growth factor. So all I would do here now is I would go ahead and multiply 4 by 1.2599, or cubed root 2. So let's go ahead and do that. So 4 times 1.2599, this gives me 5.0396. And then what we would do is go ahead and do that again to get 6.349. These are all estimates. And if I were to do that again, I would get very, very close to 8. And then so I'm going to take that 8, and we're going to go ahead and do that again. So I'm going to multiply it again by the cubed root. Sorry, I'm on my calculator. I just messed up. So 8 times 1.2599 to get 10.08. Let's go ahead and do it again. And we'd get 12.699. And then we're going to take 16, do the same thing. This would give me then 20.1584. And then finally, let's go ahead and do it one more time. And I would get 25.39. Okay, so really quickly, what number did you use as the multiplier to complete the table in question 4? Explain how you found your multiplier. So I explained my multiplier here, and all I did, like I said, is I figured out I started at 4. I multiplied 4 by the same number 3 times, 1, 2, 3, to get to 8. So that's basically saying is I would have a growth factor of 2. And to get to there, I would just have x times x times x equals 2. So when I solve for just x, I would get the cubed root of 2, which is about 1.2599. So basically, to get from 4 to 20 minutes later, I multiplied 4 by 1.2599, then multiply this number by 1.2599. And if you have a scientific calculator, guys, you can go ahead and just plug in cubed root 2 to figure out that value, okay? So it says, how can you use the equation you created in question 2 to find the value for 2 hours and 8 over 3 hours? So remember, our question in question 2 was f of x is equal to 4 times 2 to the t. So what we're going to do then here is just f of x is equal to 4 times 2 to the second power, which means, f of 2 is equal to 4 times 4, which means f of 2 is equal to 16. And your notes actually had p instead of f of x, but you guys get the idea. Okay, next one. So when you go ahead and plug this in now, I'm going to have f of 8 over 3 equals 4 times 2 to the 8/3. So this would be like 2 to the 8th power. And we're going to take the cubed root of those. So if we basically look at this then, if I just do 8 times 8 times, 2 times 2 times 2, 8 times, I would get f of 8/3 is equal to 4 times the cubed root of 256. 2 to the 8th power is just 256. So there's a few ways you can solve this. I can just bring up a scientific calculator really quickly and say what is the cubed root of 256. So if I looked at this, I will get the answer of 6.3496 times 4. And then all I need to do is multiply those two. So I'll go ahead and bring up this, multiply it by 4, and then I'm going to get the answer 25.398. 25.398. So here we go, 25.398. And if I go back and look at the table over here, I got 25.398. Perfect. So it's the same idea on how to do that, okay? So remember, this is just my power, this is my root. This is just one of many ways you could have solved it. You could have also had, the cubed root of all these 8s. Then you'd have 1, 2, 3, 1, 2, 3. So then you would have basically had 4 times 2 times 2 times the cubed root of 4. You could plug that on your calculator then as well, and to get 16 times the cubed root of 4. And then just plug that in your calculator, multiply it by 16. Like I said, multiple different ways to see that, whatever best way helps you out on that. So looking at this next one now, guys, I have this problem. What about if I have 5/3? So a detailed description, we'll just go ahead and show you to do this. If I have p equals 4 times 2 to the 5/3, always remember this is my power, this is my root. So what I want to basically have is p equals 4 times the cubed root of 2 to the 5th power. So when I go ahead now and do this, I can go ahead and solve this by just having p equals, and this would be 4 times the cubed root of 32. And when I find the cubed root of 32, let's go ahead and bring this up really quickly. I have 3174. So we're going to have 4 times 3.1748. And then when I multiply these values together, all I would do then is I would get, I'm going to go ahead and I can just bring it up right here. Go ahead then and multiply this by 4. And I'll get 12.699, just like I did on my table before. So right here, I would get the population of 12.699. And if you go ahead and look at the table like I did before, here we go, 12.699. So let's go ahead and look what Travis thought. So Travis makes the following incorrect claim. If a population doubles in 1 hour, then half that growth occurs in the first hour and the other half of the second hour. So for example, we can find the population at t equals 1/2 by finding the average of the population t equals 0 and t equals 1. So what he's basically saying is fill in the parts of the table that you've already computed and decide on how you might use Travis's strategy to fill in the missing data. Also, plot Travis's data on the resource page. Like I said, guys, you have the resource page. I'm not quite showing that, okay? So I have these values of 8, 16, 32, 64. And what he's saying is, hey, let's figure out what the average is of these. So the average of 12 and 8 would be 6. 8 and 16 would be 12. 16 and 36 would be 24, and 36 and 64 would be 48. So he's basically finding the middle of all those, okay? So while it seems like this is a plausible idea, first off, it's not, because the growth factor doesn't match in all those. You can say, well, the growth factor is 1.5, but that's you're increasing by a half and not a 1 there, okay? The other thing is you essentially have 3 different linear equations. This has its own slope. This would have its own slope. And this would have its own slope, okay? So you'd basically have 3 individual lines. So comment on Travis' idea. How does it compare to the table generated in question 1? For what kind of function would this be good? This would work fourth if the entire thing, which it's not. So if the entire problem was a linear, if the growth was linear, this would work. So for instance, if your table was like 0, 1, 2, 3, and you had 4, 8, 12, 16, you could find the halfway mark. So finding the average here of like 6. So like 6, 10, 14, that would work if the whole thing was linear. Okay? So, why is Travis's claim incorrect? Because this is an exponential graph. An exponential continues to go steeper and steeper and steeper and steeper. So between any 2 points, the slope is going to increase between those 2 points each and every time. And what Travis basically did here is he created 3 individual linear equations that would basically look like this. And that's not at a constant, every single point here, the slope is the same. Every single point here, the slope is the same. That's not how an exponential graph works. Okay? So make sure you copy all this down on the resource page. That's the entire lesson. If you have any questions, please let me know. And have a great day.